Today we are going to go over comb sort, and comb sort is a variation of bubble sort where it iterates through the array multiple times, comparing and sorting elements. Key thing is also a variation of comb sort. The difference is that comb sort doesn't start off looking at adjacent elements. So if we were to have a bubble sort, if this was our array, bubble sort would compare the current element to the adjacent one and keep doing comparing and sorting and swapping of elements. What comb sort instead does is it looks at elements at a certain number of indexes apart, and this is called a gap. Well, does this sound familiar? We had something like this for one of the other sorting algorithms, which was called shell sort. So comb sort is like combination of bubble sort and shell sort. Gap is defined as n over c, where n is the number of elements, so our input array, and c is the shrink factor, which is typically 1.3. And after iteration, what we do is we divide our gap or interval by c, which is our shrink factor, which is 1.3. And we're gonna round down until eventually the algorithm is adjacent element where gap is 1. So when gap is 1, that's exactly same as bubble sort, right? Because we're just comparing adjacent elements. Now, if it was the case that our gap was 2, so our current one will compare this one to this one, and then in the next iteration, it will compare this one to this one, and so on and so forth. On average, it works better than bubble sort, but worst case is still the same, meaning it's O of n squared. And we'll talk about our complexity soon. Like cocktail sort, it improves bubble sort by eliminating the turtles problem. And if you don't know what turtles problem is, let's say that we have an array, something like 5, 4, 3, 2, 1. And bubble sort has no problem sorting big elements because as it sorts its element, it first sorts bigger elements, which it pushes to the back, and it will second biggest to the correct spot, and so on and so forth. But it's slow to handle small numbers that are at the end of the list. Now, this number 1 will shift 1 to the left when 5 is sorted, 1 to the left when 4 is sorted, so on and so forth. So it's really slow to handle this 1. It's going to take O of n squared time. So in order to avoid this turtles problem, what we do is we have a gap so that we can potentially try to move these elements to the correct spot so that we can avoid O of n squared time complexity. Now let's briefly go over our time complexity, and again we're going to go over this later in more detail after we code our solution. But our best case is going to be O n log n. This is same as our shell sort, and the case is when it's already sorted, so we make O of n comparisons, and O of log n is the gap. Average is going to be O of n squared divided by 2 to the p power, where p is the number of increments or number of times the gap is decremented. And you will see this better next time too. And worst is going to be the same as our bubble sort, which is going to be O of n squared. And space is going to be O of 1 because we are going to use in place method for our solution. If you guys find this helpful, make sure you guys like and subscribe. Thanks. Now let's go over step by step how comb sort is going to work. Here we have our input array, so we handle positives, negatives, and duplicates. Here we have our shrink factor, which is set to 1.3, and this is how we are going to calculate our gap. So we round down, and first is going to start at length divided by our shrink factor, and these are going to be our gaps going forward. So in the first iteration, let's call it pass 1, our gap is going to be 6. Now let's bring our array here. So in the first iteration, when I is equal to 0, we're at -3, and we're going to compare it with element that's 6 gaps away, which is going to be this 0. And we check, well, do we have to swap? Nope, you don't have to swap. And we go on to next iteration when I is equal to 1, and we check our next element, which is 3, with this 0. Well, do we have to make swap? Yes, we do have to make a swap. And well, when our I is equal to 2, so we are at element -2, is there an element here? No, there isn't, right? So we finish our pass 1 and we go to our pass 2. So our pass 2 will be up here, And now our gap will be 4. Let's bring our array. And now we check our I is going to be 0 again. We check the first one with element that's 4 gaps away, which is -1. Well, do you have to make any swaps? Nope, no swaps. Now, our next iteration, we're going to check or compare 0 with 1. Well, do you have to make any swaps? No swaps, right? And we go to our next iteration, and our element is -2, and we are comparing it with 0. Well, do you have to make any swaps? No, right? No swap. Next, I is equal to 3, and we check. Do we have to make any swaps for this one? Nope, no swap. For this iteration, we didn't have to make any swaps, or we weren't able to make any swaps to be exact. Next is our pass 3, and our gap is going to be 3. And remember, I have all my gaps over here, and you're at iteration 0. Now we check -3 to element that's 3 gaps away, which is going to be 2. Well, do you have to make any swaps? Nope. And our I is 1. We check 0 with -1. Do you have to make any swaps? Yes. So we make that swap. Now we compare -2 with 1. Do you have to make any swaps? Nope, no swaps. And we compare 2 with 0. Well, do you have to make any swaps? Yep, so we do have to make a swap. And now our last iteration for this pass 3, we compare the 0 with 3. Well, do we have to make any swaps? Nope. So we're done with our pass 3, and now we move on to our pass 4. And our gap is going to be 2. So as you can see, our gap goes down from 6 to 4 to 3 and now to 2. Now we compare our first one with -2. Do you have to make any swaps? No. So we go on to next iteration, and it's going to be -1 and 0. Well, do you have to make any swaps? Nope. Keep going on, and we check -2 with 0. No swaps, and we actually don't make any swaps for this whole iteration too, and because for now everything up to here is sorted, so let's just leave it. Our array for pass 4 is going to result in this array, and we go to our pass 5, and this is going to be our last pass where its gap is 1, which is same thing as bubble sort. Now let's bring down our array, and we check when I is equal to 0. We check these two. Well, do you have to make any swaps? Nope. So we go to the next iteration. I is going to be 1, and we check these numbers. Well, do you have to make any swaps? Yep, swap. That's going to give us, and our array is finally sorted. But obviously this code will probably keep running, right, if it's not optimized. But this is our solution. So let's just go over this one more time. So we have our shrink factor, which is set to 1.3. This is how we calculate our gap. So length divided by our shrink factor, and we round out. And our gap happened to be going from 6 to 4 to 3 to 1. And for each pass, we have our gap and compare the first one with the element that's gap away. So that's I plus gap. We compare those two, and when our I increases, our gap, I plus gap also increases. And we obviously stop when we hit our last element, because if you wanted to keep going, there will be no elements, and this will be just undefined. So we move on to our pass 2, which is going to have a gap of 4, and we do all the same thing where I is going to start at 0, and we compare it with I plus gap, and we do that for all the elements, and then we just keep moving, repeating the same thing over and over again until we get our finally sorted array. And remember that when our gap is 1, that's equal to bubble sort. Now, before we code our solution, let's go over our pseudocode first. When you read the pseudocode, you should notice that, again, this is going to be really similar to our bubble sort, and the reason is obviously because this is a variation of bubble sort. But regardless, let's go over our code. First, we're going to create a function that takes in our input array, and we're going to create a swap function, which I already did, and we're going to declare a variable named shrink factor and set this equal to 1.3. And we are going to use this to calculate our gap. Next, we want to store a variable to store our gap, and you're going to set it to the length of the array initially. Next, we want to create a variable named swapped so that we can check if we made a swap or not. If we didn't, we want to just exit out of the loop to save time, and we are going to set this to false. Next, we're going to create a do while loop, and this is going to run as long as swapped is true and gap is greater than 1. And the reason why gap has to be greater than 1 is because you can't compare a number to itself, right? Let's say that it was 0. So that means that the index and the gap will be the same thing, then they'll be pointing to the same element, which is impossible. You can't make comparisons like that. And next, we want to calculate our gap, and our gap is going to be gap divided by the shrink factor, and we are going to round down. Next, you want to iterate to all the elements as long as index plus gap is less than the length of the array. And we have to have this checked, because if we didn't have this, we might be comparing elements that's out of our array. Like, let's say that the length was 4, and we might be checking element at index 5, which is not gonna work. And next, we want to check if element at index I plus gap is less than our current one. And if it is, we are going to swap and set swap to true. And when we are done iterating through the whole thing, we want to return our sorted array. So given that, try to code this solution yourself. If you're not too familiar with how bubble sort works, I really recommend you to watch the previous video to get a better understanding and come back to the solution later. Now let's start coding our solution. First thing I want to do is I want to create a variable for my shrink factor, and this is going to be set to 1.3. Next, I need to declare my gap, and we are going to initialize it with the length of the array. That looks good. Next, I need to create a variable named swapped. This is going to check whether we made a swap or not, and we are going to give a value of false. Next, let's create our do while loop, and this is going to run as long as swapped is true and gap is greater than 1. And later we are going to return our array, and it should be swap. Okay, looks good. So first thing we're gonna do is we're gonna recalculate our gap. So gap is going to be gap divided by the shrink factor. Also have to round down our gap. So math.for gap. Okay, that looks good. And we are going to iterate to all the elements in our array starting at index I, and we're going to iterate until I plus gap is less than the length of the array. Because if it was bigger, that means that we are pointing to an index that's outside of our array, and that will just be undefined. Next, we need to check if our element at I plus gap, if this is smaller than our current element, so array at I, what do you want to do? We want to swap. So pass in our array, our index, and our other index, and then we set swapped to true. And that's it. That's all there is to comp sort. So we have our sorted array, and let's just uncomment this to check if it really worked. And starting from -98 all the way down and down, you can see that everything's sorted. So all the way from -98 to 100. Now let's just uncomment this and go over our code one more time. So we have our usual swap function. We made our shrink factor, we set our gap to the length of the array, and then we set swap to false. Now we created our do while loop, and we recalculate our gap every time, and this is going to be rounded down, and it's going to be gap divided by the shrink factor. And if I were to just console log gap, our gap is exactly the same as our illustration. So 6, 4, 3, 2, and 1. So that's good, right? And we are iterating through our array, starting at index I, and until I plus gap is less than the length. And this is really important because we don't want to go outside of our array, because there wouldn't be any elements, right? Or if you wanted, you could have just done this. Just I is less than array length minus gap, which is totally the same thing. It's really up to you, whichever one makes more sense. Next, we check, well, is our element at I plus gap less than our current? And if it is, it's out of order, right? So we swap, and we set swap to true, and we keep going on until swapped is true and gap is greater than 1. And finally, we return our sorted array. So that's it for comp sort. I hope that helped, but you should notice that really everything's same as our bubble sort. It's just this line that's different, this condition that's different, but other than that, it's pretty much the same, right? Now that we finished solving for our solution, let's go over our time complexity and space complexity in a little more detail, because I think we should now have a better understanding of how comp sort work. The best time complexity is O of n log n, and that's the case when the elements are already sorted. So we are going to make O of n comparisons, and our O log n comes from gaps that we make, or the gaps that we get. So O log n is pretty much the outside do while loop, and O of n is the inner for loop, the comparisons that we make. Now the average is O of n squared divided by 2 to the power of p, where p is the number of increments or the number of times the gap is decremented. So our gap was, I think, 6, 4, 3, 2, 1. So we had 5 decrements. So it will be 2 to the 5. And worst case is O of n squared, and this is same as our bubble sort. And finally, our space complexity is O of n because we are using in-place method to solve for our solution. If you guys find this helpful, make sure you guys like and subscribe. Thanks.